Good morning, everyone. Welcome to the session of membrane distillation. First, we have our keynote speaker, Alison McGuffey from Princeton University. She'll be giving us a talk on the merits and metrics of wetting in membrane distillation. And I'll hand over the session to you, Alison.
Great, thank you so much. Let me just share my slides here. Great, can you see my slides? Should be good.
Should be good.
Okay. All right, so yeah, thank you all for being here today. I'm very honored to be giving this talk. So currently I'm a postdoc at the Andlinger Center at Princeton University, and the work I'm going to be talking about today is from the tail end of my PhD work with Professor Amy Childress. So I'll get started with some motivation and background. So as I'm sure everyone here is very familiar, interest in the desalination and reclamation of increasingly challenging higher and higher salinity streams is growing. And we would, of course, generally prefer to use reverse osmosis for these applications because reverse osmosis is the most energy efficient desalination technology. Reverse osmosis is salinity limited, at least currently. And thermal desalination processes, in contrast, are able to treat high salinity streams. So that brings me to membrane distillation, or MD. So in MD, we have a warmer saline feed stream and a cooler pure distillate stream separated by a microporous hydrophobic membrane. And the temperature difference across the membrane causes water from the feed stream to evaporate at the membrane surface, diffuse through the pores in the vapor phase, and condense upon reaching that cooler distillate. So there's a few advantages of MD. It's been shown to potentially be more efficient than conventional thermal desalination processes, especially at smaller capacities. MD can also utilize lower grade thermal energy, and MD is modular with a relatively low capital cost and a small footprint. So this is a SEM image of a typical commercial PTFE MD membrane. The morphology is characterized by the strands of polymer material here, which we call fibrils, and they intersect to form pore openings. And this just shows a schematic of an idealized and simplified version of the membrane structure. So if we imagine a cross-section of that idealized structure, it would look something like this, where we have the feed stream and the distillate stream separated by a vapor gap, which is supported by the membrane. That vapor gap allows us to, in theory, achieve 100% rejection of non-volatile solutes. However, if pore wetting occurs, liquid can penetrate through that pore, resulting in the diffusion of solutes and particulate matter smaller than the pore size through the membrane. So when pore wetting occurs, solute rejection is not achieved. So there's some goal to understand the wetting resistance of MD membranes. And in many cases, researchers rely on what I'm calling ex situ indicators, just referring to parameters that are measured outside the MD process. So contact angle, of course, is used to characterize membrane hydrophobicity. Either the intrinsic or the measured contact angle on the membrane itself are frequently used. And liquid entry pressure, or LEP, is commonly used to characterize wetting resistance. So LEP is defined as the minimum transmembrane pressure at which point liquid is forced through an unwetted pore. And according to the classic models, LEP is understood to depend on the surface tension of the feed solution, the contact angle of the membrane, and the pore size R, which for the minimum LEP, which is generally reported, corresponds to the maximum pore size. So both LEP and contact angles are typically measured using clean or pure water at ambient temperature. But in membrane distillation, the elevated temperatures, elevated salinities, and elevated pressures can affect the interfacial tensions and contact angle, which affects LEP. LEP also does not consider the wetting mechanisms that occur during MD, and I'll mention those on the next slide, but applied pressure, as is used in LEP measurement, affects the membrane surface uniformly. Concentration polarization, and especially scaling and fouling, may not. They can be heterogeneous on the membrane surface. So in these cases, wetting may not initiate at that largest pore, the maximum pore size, but instead where scaling or fouling is most severe. So in a previous study, we reported, or introduced rather, the LEP distribution based on the pore size distribution to better predict wetting. But these ex situ metrics have limitations, and they may not accurately describe wetting that occurs in situ. So the mechanisms that are most relevant to MD include alcohol and surfactant-induced wetting and fouling and scaling-induced wetting. So I've grouped alcohol and surfactant together, not because they're identical, but because both are associated with surface tension effects, and fouling and scaling-induced wetting are both associated with membrane surface effects. So if surfactants or alcohols are present in the feed solution, they can accumulate at the feed-vapor interface due to concentration polarization, which results in a lower surface tension of the feed, which reduces the LEP and can drive wetting. If fouling and scaling or scaling occurs, then crystals and foulants can deposit or grow on the membrane surface, which can reduce the effective hydrophobicity of the membrane, which reduces LEP and can drive wetting. So pore wetting is a key concern for these industrial wastewaters that MD is often suggested for, because in many cases they contain surfactants or alcohols and/or can cause fouling or scaling of the membrane. So for this study, we're interested in looking at in situ indicators to better understand wetting that occurs during MD. So currently studies most often use increases in the distillate conductivity, which is measured, or decreases in rejection, which is calculated from conductivity, to indicate wetting. Now in theory, as I mentioned, MD achieves 100% rejection, but in practice, we typically measure values slightly less than 100. So researchers have used arbitrary definitions of low rejection to define wetting. So when the membrane is dry under ideal conditions, we have vapor flux occurring from the feed to the distillate side, and that condensed vapor accumulates as product water or distillate, and from that we can determine net flux. However, when the membrane is wetted, we not only have vapor flux, we also have liquid flux, and with that solute flux through the membrane. And so this is, of course, implicitly understood in the MD literature, but not typically explicitly acknowledged. But when we have liquid flux, we not only have condensed vapor, distillate, accumulating, but also liquid permeate accumulating in our product water. So for that reason, I'll refer to this as the distillate permeate stream for short, just to acknowledge that. And of course, in that case, net flux depends on both the condensed vapor and the permeate passing the membrane. So the objectives of this study were to quantify both liquid flux and vapor flux during MD and introduce liquid flux as an in situ wetting metric, to define modes of wetting in MD and to look at the effect of membrane properties on those modes, and to evaluate trade-offs between liquid and vapor flux. So that brings me to materials and methods. So this shows a schematic of the bench scale system we used in this study. I just want to note that we do operate with a constant volume in our distillate permeate tank. So as liquid accumulates in product water, it immediately overflows into this vessel, and we measure that mass continuously to determine net flux. So in order to determine vapor flux and liquid flux, we just used a very simple solute mass balance. So we equate the mass of the solute entering the distillate permeate stream, which only occurs due to wetting, with what accumulates in the system and what exits in our configuration due to the overflow here. So if we equate these mass terms to concentration by volume, we obtain this, and we can determine solute flux simply as shown here. And liquid flux finally is obtained just by using the known density and the known concentration of the feed solution. And then vapor flux is very simply obtained by subtracting liquid flux from net flux, with everything being in units of mass per membrane area per time. So we make a few simplifying assumptions here. So we assume that liquid flux occurs from the feed to the distillate side. We assume that the liquid wetting the membrane is at a solute concentration equal to the feed solution at the membrane surface where wetting occurs. And we assume that both streams are well mixed. So on to results here. So I first want to talk about results under baseline conditions. And this is a commercial PTFE membrane. And here I'm showing the contact angle, the maximum surface pore size, and the bulk porosity. So for our baseline tests, we use a 1 molar sodium chloride feed solution at an ambient, or rather moderate temperature. So here I'm showing the concentration of our distillate permeate stream in milligrams per liter sodium chloride, and I'll refer to this as CDP for short. So we see initially the CDP increases, and then after about 11 hours, we reach a steady, stable concentration. And here I'm showing the net flux and the vapor flux. So we can see at this scale that net and vapor flux are nearly equivalent. So they overlap here. They're also relatively constant throughout operation. And finally, we have our liquid flux. So here, kind of curiously, liquid flux appears to decrease initially. And then after about 11 hours, it's approximately 0. So we know in MD that liquid doesn't stop diffusing through a wetted pore without intervention. So this suggests that something other than wetting is occurring. So if I bring back our bench scale system here, when we complete an experiment, we drain our distillate permeate tank and we rinse the tubing and tank with deionized water, in our case until conductivity is below 2 microsiemens per centimeter and stable for several hours. And then when we begin a new experiment, we of course replenish this tank and begin pumping. So if any higher salinity water remains in the heat exchanger, the probe fittings, then that will begin to mix as we pump, which results in an initial increase in concentration. And then when the stream is fully mixed, a stable concentration. So we're attributing this to solute mixing, which is indicated by increasing CDP, but apparently decreasing liquid flux. And this is an experimental artifact, not indicating pore wetting or membrane performance. And we believe this is not unique to our system, but likely common in recirculating systems and may account for some of the non-idealities in rejection that have been previously observed. And I'll also mention quickly that if we had operated for 5 hours or less, which is commonly reported for initial membrane performance, based on CDP alone, this would appear to be wetting. However, if we look at liquid flux, we can see that decrease and we know that it is not wetting. Okay, so now on to actual wetting results. So this is a second commercial PTFE membrane. It has a similar contact angle and similar bulk porosity, but a larger pore size. And we also operated here under baseline conditions. And we see that CDP increased steadily in this case throughout operation. Net and vapor flux also are very similar. They overlap here throughout operation. They're also relatively constant. And then in this case, liquid flux is also relatively constant throughout operation. So this suggests that one or more pores wetted initially and remained wetted throughout operation, resulting in this constant leak of liquid through the wetted portions of the membrane. And we can also note here that liquid flux is about 2 orders of magnitude lower than vapor flux, which suggests that most of the membrane remained dry. So most of those pores were only allowing vapor through, and only a few pores were wetted. So at constant liquid flux, we call this constant wetting mode, indicated by increasing CDP at constant liquid flux. And we can also predict the final concentration of our product water simply by assuming constant vapor flux and constant liquid flux continues after our 24 hours of operation. And for this membrane, we obtain about 3.5 milligrams per liter sodium chloride in our final product water. And notably, that may meet quality requirements depending on the application. So in this case, wetting may not require intervention. Constant wetting can be tolerable. And before I get on to the next portion of the talk, I want to first look at liquid flux in comparison to rejection, which has been commonly used. So here at the top, I have the QMO5O membrane that did not wet, but we did observe solute mixing effects. And below the QL822 membrane, which wetted under constant wetting mode. So in both cases, rejection is actually relatively constant. So rejection does not show these wetting trends as clearly, and that's especially true for these cases where liquid flux is very low for identification of wetting early on and for initial identification of low wetting rates. And also we can note that if we look at the slope of the conductivity of our distillate permeate stream, the trend is in both cases virtually identical to liquid flux. So slope of conductivity can be a proxy for liquid flux, but without these meaningful units, so we can't understand wetting rates quantitatively or compare to vapor flux. Okay, so we also looked at some different solution chemistry effects. So here is a third commercial PTFE membrane, and it again has a similar contact angle, similar bulk porosity, but an intermediate pore size. And this top row shows performance with a surfactant containing feed solution. So we saw that CDP began to increase pretty early on and increased rapidly. we see that net and vapor flux initially are very similar, they overlap, but at longer operating times, vapor flux is slightly lower than net flux, suggesting that more pores were wetted. And then if we look at liquid flux, we now see that liquid flux increases over time. And this suggests that at our constant operating conditions, more and more pores were becoming wetted, resulting in more and more liquid flux. And this is likely due to increasing bulk concentration of surfactant. We also looked at a high salinity feed solution using sodium chloride as a model scalant. And we see that pretty similarly, CDP increases relatively early and more rapidly. And we see that net and vapor flux, in this case, are similar and overlapping throughout operation, indicating that most pores remain dry. But again, if we look at liquid flux, we see that once wetting occurs, it increases over time. So for that reason, we're calling this increasing wetting mode, characterized by increasing CDP and increasing liquid flux. And notably, this will eventually require intervention as CDP will exceed our product water quality requirements at some point. So we also were interested in how membrane properties affect wetting. And here I'm showing results for pore size. So here I've just repeated the results from the previous slide for our QMO22 membrane with the high salinity feed solution. And we also looked at the performance of our QMO50 membrane, which was our good membrane that did not wet under the same conditions. So here we see that although we've delayed increases, we still see a relatively rapid increase in CDP. Net and vapor flux for this membrane, also very similar and overlapping throughout operation, indicating that most of the membrane did remain dry. This decrease is likely due to scaling of the membrane surface. And similarly with liquid flux, we see a delay, but we still see this increasing trend. So we saw increasing wetting for both. Despite differences in pore size, both of these membranes wetted at increasing wetting mode. And the last thing I want to mention today is looking at how membrane thickness affected wetting. So for this, we used electrospun membranes. And here I'm showing the contact angle, maximum surface pore size again, and also the membrane thickness. And we tested these again under our baseline conditions. So here we see results for CDP versus time. And we see that this membrane wetted relatively quickly after just about an hour of operation, and CDP increased relatively rapidly. We see that net and vapor flux initially are very similar and overlapping, suggesting the membrane was dry or mostly dry. And eventually, vapor flux was slightly lower than net flux. And if we look at liquid flux, we see this increasing trend. So here for the first time, I'm showing increasing wetting mode under baseline conditions. So not associated with solution chemistry effects, but with some material property. And because these membranes had a relatively similar contact angle and pore size compared to the PTFE membranes I showed earlier, we are attributing this or hypothesizing that this is due to a different membrane property, and it's likely due to high pore interconnectivity, or in other words, permeability of the membrane parallel to the membrane surface. So one or more large pores may have wetted, and then liquid was able to permeate to adjacent pores due to high pore interconnectivity, resulting in wetting of more and more pores over time, resulting in greater and greater liquid flux, even at baseline conditions. So we next looked at a second electrospun membrane, which was spun under the same conditions with the same material, but for a longer amount of time. So resulting in a similar contact angle, similar pore size, but a greater membrane thickness. And here I am expanding the time axis from 3 hours now to 30 hours. So we saw that CDP increased much more slowly, but steadily throughout operation. Net and vapor flux for this membrane were similar and overlapping throughout operation, indicating most of the membrane did remain dry. And then when we look at liquid flux, we see a delay, but we again see that increasing trend in liquid flux. And here I'm expanding the y-axis to make that more clear, so we can see liquid flux increases over time. And finally, we tested a third electrospun membrane. Again, similar contact angle, similar pore size, but greater membrane thickness. And now expanding our time axis to 55 hours, we see that although it increases more slowly, CDP increases steadily throughout operation. Net and vapor flux are similar and overlapping throughout operation. But liquid flux, although we did get a longer delay, we still saw that increasing trend in liquid flux. So similar to pore size, we saw that thickness apparently does not affect the wetting mode. And we can also see here a trade-off between vapor flux and liquid flux due to membrane thickness, which is not typically understood to affect liquid entry pressure. So this is kind of interesting. So we see that as membrane thickness decreases, we obtain a higher vapor flux, but at the same time, wetting is more severe and occurs earlier. So that brings me to my conclusions. So here I'm just showing all of the data that was used in this paper, including the polypropylene results that I didn't quite have time for today. But we saw increasing CDP at decreasing liquid flux, especially at short operating times. And we attribute that to solute mixing, which is an experimental artifact that may be common in recirculating systems. We saw increasing CDP at constant liquid flux, and we call that constant wetting mode, which we showed in some cases may be tolerable. We saw increasing CDP with increasing liquid flux, and we call that increasing wetting mode. And we saw that that was associated with solution chemistry effects for surfactant, as well as scaling induced wetting, independent of membrane pore size. And finally, we saw increasing CDP at increasing liquid flux under baseline conditions for certain membrane materials. And we're hypothesizing that this may be due to high pore interconnectivity, which is a subject of ongoing study in the Childress Research Group. And with that, I will conclude just by quickly acknowledging the funding for this talk, or for this work rather. So this was funded by an NSF grant. I was also supported by these fellowships during my time at USC. Parker Performance Materials supplied the PTFE membranes that we used. Of course, thank my research group and the Smith group for supplying the electrospun membranes that we used, and my current research groups, which are the Priestley Lab and the Princeton Wet Lab. So with that, I'd be happy to take any questions. Thank you.
Thank you, Alison, for this interesting talk. Is there any questions? Fei Guo has asked, I have two questions about the electrospun membranes. What is the material you make the ES membranes? I saw some beads in the SEM images of the ES membranes. Do you think whether the beads can affect the wetting?
Yeah, those are great questions. Thank you for asking that. So the material we used was a blend actually of PVDF as well as PVDF HFP, hexafluoropropylene, I think. And so it was a relatively hydrophobic material, but yeah, we did see these beads, and that was an issue that we didn't end up optimizing for. I do think that that may have affected wetting and potentially opened up larger gaps in the membrane, maybe giving it a larger effective pore size than what we characterized by, providing this large chunk of polymer material, but opening up gaps potentially below it or around it. So that's not something we looked at, but it's a really good point. So thank you for that.
Thank you, Alison and Faye. Is there any other questions? So I have a quick question about what is your recommendation for fabricating a membrane that is suitable for membrane distillation?
Yeah, that's a great question. And that's something that I think this work definitely leads to. So I think that reducing pore size is something that has been less explored in the literature than just increasing the contact angle of the membrane, but could be a more robust way to impart wetting resistance, especially for scaling induced wetting. And that's something that also my previous paper kind of led to. So, and then also increasing membrane thickness might be a way to kind of maintain the materials that are lower cost, but less hydrophobic or easier to work with, not these perfluorinated materials. So we can mitigate liquid flux without increasing the surface hydrophobicity as much. So I think those are two avenues that might be able to increase wetting resistance. Thank you.
Okay, thank you, Alison. So I'll move on to the next speaker. Thank you, Alison. Right. So our next speaker is Jingcheng Cai from Dalian University of Technology. He'll be giving us a talk about membrane failure analysis in membrane distillation processes. So I'll hand over the session to you, Jingcheng.
Okay, thank you. My name is Cai Jingcheng. I'm from Dalian University of Technology. I'm a student of Professor Fei Guo. His presentation will be in the afternoon. Our first work is membrane failure analysis during membrane distillation processes. According to the terminology of membrane distillation, no condensation should take place inside the post of the membranes, as that may cause membrane failure. This study, we focus on the condensation in the membrane post under certain conditions during MD processes. Commercial hydrophobic PTFE membrane were used in this work. The membrane morphology was characterized by SEM, and a lab scale REP unit was to measure the liquid entry pressure. The pore diameter, contact angle, porosity, and the REP will show in the table. And air gap membrane distillation system was used in our work to measure the membrane distillation OMD performance. We started our study from the observation and confirmation of membranes in the membrane processes to confirm the membrane failure. We started our first experiment with the membrane thickness 105 micrometer. Then under the we see some bulges in the membrane surface, and the membrane weight of after MD test is 37.67 grams, and that after drying was 33.59 grams. That's the water that the condensate is inside the membranes, and it may cause the bulges in the membrane surface. The membrane used in this work then is PTFE membranes with the pore size of 1.22 micrometers, and the Nielsen number is 1.65. That's the transition diffusion is used to describe the mass transfer. The experimental data is not agree with the theoretical estimations. The p-values established from Nielsen diffusion decreased about 5%, and established from molecular diffusion and the transition diffusion increases with the temperature. But in our experiment, the p-values decreases about 37%. And we start another experiment at a fixed temperature of feed of 70 centigrade and a current temperature of 20 centigrade, and run for 12 hours. That's as usual, the permanent flux and B value should be kept constant, but in our test, the permanent flux and B value decreases with the running time. The mass of the MD module is after MD test was 40.13 grams, and that after drying was 37.87 grams. That's the condensate is also happened in the membranes. That's we may draw a conclusion that the decreasing tendency of B values in the BT diagram may indicate the condensation occurs in MD processes. The condensation inside the membrane pores we can show in the following mechanisms. The cylinder pores, the mass transfer in the cylinder pores can be described by Darcy's law. In the hydrophobic membranes, when condensation happens, the mass transfer should be described in the following pictures. In a hydrophobic membrane, the contact angle is higher than 90 centigrade, that's the condensation pressure may be higher than the saturated vapor pressure. That's the condensation inside the membrane pores may decrease the driving force of MD. That's the B values established by Darcy's law from the permanent flux, and the feed temperature and the coolant temperature may be decreased. The condensation is more likely to occur in MD with a high feed temperature and thick membranes. In this experiment, we use three kind of membrane thickness. In the membranes with a thickness of 80 micrometers, the B values keeps constant and no bulges in the membrane surface. There's no condensation in the membranes. In the membrane thickness with for the membrane thickness of 112 millimeter, the B value decreases significantly, and the large number and the diameter bulges in the membrane surface, that condensation occurs in the membrane surface. That's a significant decreases in the B values, indicates a large number and the diameter of bulges. That's the condensation occurs inside the membrane pores. This is because the thick membranes or high temperature also leads to a large temperature difference across the membranes. That the pressure gradient across the membrane increases. That may lead to condensation inside the membrane pores. Another work we do is for different coolant temperature. That's the condensation is more likely to occur in MD with low coolant temperature. For the temperature keep at 35 centigrade, the membrane surface keeps flat and no bulges in the membrane surface. And an increase of B values indicates no condensation occurs inside the membrane pores. For the membrane, for the MD processes with coolant temperature keep at 5 centigrade, the membrane surface shows some bulges. That's a significant decreases in the B values also indicates a large number and diameter of bulges. And this is because the low coolant temperature also leads to a higher temperature difference across the membranes. That's increase the temperature difference across the membranes. A lower coolant temperature increases the number and the diameter of the bulges. Through our experiment, we found the higher temperature can reduce the probability of condensation inside the membrane pores. And it also has a very little effect on the permeable flux. The condensation is more likely to occur in MD with small air gap wise. The air gap has the air gap has a very significant effects on the mass transfer and his transfer in MD, in AGMD. For the membrane with 4 millimeter air gaps, the membrane keeps flat and no bulges in the membrane surface. The B values keeps constant. There's no condensation in the membranes. In a smaller air gap with the air gap of 1 millimeter, the membrane bulges very significantly. That condensation inside the membrane pores. That's the smaller air gap wise increases the number and the diameter of the bulges. Compare with the air gap and the feed temperature, coolant temperature, we found the influence of air gap is greater than the membrane thickness, feed temperature, and coolant temperature. This is because the heat resistance comes mostly from the air gap in HMD system. The temperature difference across the membrane increases significantly with the decreasing air gap wise. We do our final work is on the multi-layer membranes. We found the condensation is always happening in the multi-layer membranes. For the single membrane, we use the thickness of 80 micrometer. There's no condensation in the membranes. That's the condensation effect that can be neglected. That's we found a significant decreases from 40 to 70 centigrade. with 2 layers and 3 layers membrane MD processes. The significant decreases in the p-values indicates the condensations occurs in the gap between the membranes. This is because the water vapor decreases in the temperature during the expansion from a membrane pores to a thin gap between the membranes. The thermoconductor resistance exists at the membrane interfaces and reflects itself in the jump in the temperature field. Through our experiment, we drew the following conclusions. Condensation in the membrane pores can happen under certain conditions during MD processes and leading to membrane failure. The condensation is more likely to occur for the membranes with large thickness, high porosity, low thermal conductivity, small intrinsic vector contact angle, large pore size, and multi-layers. Some operating conditions can also cause condensation due to the MD processes such as high feed temperature, low coolant temperature, and small air gap. The decreasing tendency of p-value in BT diagram indicates condensation in the membrane pores. The mass transfer processes can maintain a dynamic equilibrium in the pores when condensation takes place. Condensation in the membrane pores can decrease the membrane performance in terms of permeable flux by reducing the driving force for membrane transfer. That's all, thank you.
Thank you, Jingcheng, for your interesting talk. Is there any questions regarding Jingcheng's talk? So, Jingcheng, I have a quick question for you. Is there any conductivity, or did you do any tests in the saline effluent in your test? Did you test your membrane, your membrane distillation operation for any salt solution?
Yes. This is the feed was used the sulfur, copper sulfur, copper sulfur solutions, and the concentration is 3.5 mass. The mass concentration is 3.5%.
So what is the relationship between increasing the air gap and the conductivity change in your permeate?
Sorry, I can't.
Also, by increasing the air gap, you say you can decrease the failure rate for membrane distillation, right? So,
Yeah.
what is the conductivity change in the permeate if you increase the air gap? Did you also analyze that?
We didn't analyze in this work, but we do some analysis in the other works that the air gap increases and the temperature difference across the membrane decreases significantly.
Okay. All right. Thank you.
Thank you. Thanks for your questions.
I have a quick question as well. I was wondering, I think I've read in some previous papers that system shutdown or intermittent operation can be associated with condensation in the pores. Is that something you guys looked at or you can comment on?
Thanks for your question, but can you slow down? I
sorry.
sorry.
Of course. Yeah, I was just referring to like system shutdown. So like turning the temperature gradient off, turning your heater off so that the temperature difference across the membrane goes away. And I've read, I think, some papers that mentioned that wetting can occur when the temperature gradient is paused or stopped. So for like intermittent operation, like if you're turning your heat source off and on.
Mm. I'm sorry, but I don't. I
No
actually.
worries.
I think Alison meant if you stop your operation, like if you stop your operation, then if you start it again, you might expect a wetting during that time because there might be some condensation inside the pores. Do you agree with that? What's your opinion about that?
That may happen, but when we stopped our experiment, we take the membrane module out and we weight the membranes and we found the bulges in the membrane surface. That may happen when we stop the MD process, that the conditions changed significantly. That may cause the condensation inside the pores. But we do another experiment with electrical spinning membranes. We will use acrylic modules that we can see the membrane surface, and we also find some bulges on the membrane surface. That's the membrane width also increases. That's the way think the membrane the bulge is always happened may happen in the condensation may happen in the MD processes.
Okay, thank you, Jing Cheng.
Okay, okay, thank you.
Okay, great. I think it's about time to move on. So our next speaker is my co-host, Wenwei Zhang, and she is going to be speaking about membrane distillation, wetting by naturally existing surfactants in traditional Chinese medicine, or TCM extracts. So I think we have a recording for this, so we'll get that going.
Good morning, everyone. I'm Wenwei from Guangzhou Institute of Advanced Technology. I'm honored to be presenting our recent work on wetting by naturally existing surfactants in traditional Chinese medicine solution by direct contact membrane distillation. As this is a session dedicated to membrane distillation, I will skip the introduction on the general principle of membrane distillation. Without further ado, let's begin. Membrane distillation has been an emerging desalination technology for water treatment. We've noticed a growing research interest in the concentration by MD in food and pharmaceutical processing, such as fruit juice and maple syrup. MD has also been applied in the water removal for herbal and TCM extracts. However, we know that there are large amounts of naturally existing surfactants present in the herbal extracts. They might cause membrane wetting. Membrane wetting is one of the major issues hindering the application of MD in the industry. Wetting could cause direct liquid penetration and failure to the concentration process, as the bioactive compounds can pass through the membrane. It was believed that wetting could happen when the liquid entry pressure is lower than the transmembrane pressure, or the absorption of the amphiphilic compounds rendering the hydrophobic membrane to hydrophilic. Although surfactants could lower the surface tension of the solution, recent studies suggested that wetting criterion of the transmembrane pressure to be higher than the liquid entry pressure might not be applicable in surfactant-induced wetting. In the surfactant-induced wetting case, wetting is not instantaneous, it's transient, and wetting behavior is highly related to the surfactant properties. This could mean that solution environment is critical to determine the wetting behavior of the membrane. It is important for us to also note that in the TCM extract, the solution chemistry is extremely complicated. Although saponins are known as the surfactants typically present in herbal and TCM extracts, the chemistry of the saponin is hard to identify, especially whether they are ionic or not. That means the interaction between the membrane and the surfactant in the aqueous environment is hard to predict. Hence, in this study, we would firstly like to characterize the model TCM solution made up with saponin, and we performed a static absorption test on the PVDF membrane in the model TCM solution. And later, we performed a dynamic concentration test by MD in the model TCM solution. This is the operating conditions selected for this study. The data was collected in the custom-built DCMD configuration every 1 minute. We selected 3 typical saponins abundant in herbal plants and TCM. They are T-saponin, ginseng saponin, and glyceric acid. We noticed that GA solution was very viscous at higher concentration. The linear correlation between the concentration and conductivity confirmed that all 3 selected saponins in this study are non-ionic surfactants. By measuring the surface tension of the solution at different concentrations, we determined a range of CMC values for the 3 saponins. CMC is also known as critical micelle concentration. It's an important factor for surfactants as it gives information on the surface tension of the solution at a given concentration. The surface tension of GS and TS were similar above their CMC values. Their zeta potential values were also similar. During the static test for PVDF membrane in T-saponin solution, we chose a value of 0.1 and 1 gram per liter as the concentration below and above the critical micelle concentration. We observed that PVDF membrane showed little absorption affinity to the T-saponin solution in both cases. However, complete absorption was observed in T-saponin solution of 10 grams per liter after the 24 hours test. We were also interested in the absorption behavior of genus PDA modified PVDF membrane during a static test, and we observed that the PVDA-coated PVDF membrane was able to resist the TS absorption for 24 hours during the static test. Then we conducted a series of dynamic concentration tests in TS solution at a concentration of 1, 5, and 10 grams per liter. We found that gradual wetting happened at 4 hours in the highest concentration, and the permeate conductivity slowly increased to the same value as the feed solution. We suspected a complete wetting at the end of the experiment. In the test of 5 grams per liter, gradual increase in permeate conductivity was observed from 15 hours onwards. However, the conductivity did not continue to rise up to the level of feed solution. Although we couldn't see a rapid increase in the conductivity change in the 1 gram per liter test, flux decline was significant in the TS solution. And we conducted an SEM analysis on the membrane surface after the test. We confirmed that the pore on the permeate side was completely blocked by a layer of deposition. Later, we also conducted a dynamic concentration test in the GS solution with PVDF membrane, and we observed a similar trend of wetting behavior. However, we did not see a flux decline in the GS solution at low concentration. We were also interested in the PDA-coated PVDF membrane on the wetting resistance in the TS solution at 10 grams per liter. We found that although PDA membrane showed little absorption affinity in the static test in the TS solution, complete wetting was still observed within 24 hours during the MD operation. Wetting initiated at roughly the same time as the PVDF membrane, but PDA-coated membrane could postpone complete wetting. We conducted a contact angle measurement on both the membranes from the dynamic concentration test. Both membranes showed a drastic reduction in the contact angle, but the PDA-coated membrane had a higher contact angle values. We suspected that the rate of TS absorption might be lower in the PDA-coated membrane. We highlighted these findings from the work I introduced just now. T7 absorption onto the PVDF membrane was significant at much higher concentration of its CMC value. The wetting behaviors of the PVDF membrane in TS and GS solution were similar regarding their similar properties at high concentrations. It is still unclear what might have caused a difference in the dynamic test in TS and GS solution at low concentration. PDA-coated PVDF membrane might be able to postpone the complete wetting, while the time taken for the occurrence of wetting was similar to PVDF membrane. Due to time limit, I'm only able to show these results with you all. In the end, I would like to appreciate the work done by our students who were affected by this COVID situation and could not return to Australia. Wan Yu and Ming Zhang, previous student at University of Sydney, and Xiao Wei, current undergraduate student at UNSW. She's also looking for PhD opportunities. This project was funded by National Key Research and Development Program of China and China Postdoctoral Science Foundation. Thank you all for listening.
Great, thank you so much for that talk. If there are any questions, feel free to type them into the Q&A or the chat. I'll get us started off here. I was wondering, do you think there's any role of surface roughness in sorption of surfactants on membranes other than just intrinsic contact angle?
Oh, I think so too. So we probably are going to look into that too.
Great. Thank you.
Thank you.
Let's see if we have any other questions for the speaker, feel free to type them in. I was also curious about the wetting curves you observed for conductivity, kind of showed a slow increase and then this sharp breakthrough before it reached the complete wetting. Can you comment on why you think that is?
Right. So the experimental setup was done by using a conductivity meter that's dipped into the permeate stream. So we might think that the conductivity meter might not be that sensitive. So that's why we also use the line to connect the points. So we observe that the conductivity of the permeate that's probably around 30 or and then it jumped up very drastically at some point. So not sure if that's due to the sensitivity of what we have in our lab. So we might want to further analyze what's also causing that too.
Yeah, that makes sense. Thank you so much.
Yeah.
Okay, I think it's actually time for us to move on
right.
to our next speaker. Thank you so much, Wenwei. So our next speaker is Fengshu Chu, and who will be speaking about performance and membrane fouling during landfill leachate treatment using direct contact membrane distillation, a comparison of young and aged landfill leachate. So Fengshu, I'll leave it to you.
Okay. Okay. Okay, Alison, thank you for your introduction. Good morning, good morning, dear friends. My name is Fengshu Chu. I'm from Guangzhou University. I'm glad to introduce some of my work here, but it's a pity that we cannot meet in Shanghai and discuss some interesting topics face to face. My topic is about landfill leachate treatment with membrane distillation, performance, and membrane fouling. As we know, urbanization is becoming faster. More and more people live in cities. This may lead to generation of a large amount of municipal solid wastes. To protect the environment, sanitary landfill is used to treat the municipal solid wastes, but this may cause the problem of landfill leachate. As we know, landfill leachate has many problems like high in quantities, high in ammonia concentration, and low in biodegradability. Until now, landfill leachate has become a huge challenge in the field of wastewater treatment. Landfill leachate treatment usually require a long chain of treatment process, including physical, chemical, and biological treatments. And membrane technologies like ultrafiltration and reverse osmosis are usually used for landfill leachate treatment. But this will have some problems like very serious membrane fouling and high energy demand. These problems prevent the membrane technology from the application in the landfill leachate treatment. Usually, we want to develop some simple process or some one-step separation for the landfill leachate treatment. And membrane distillation is such a technology which attracts a lot of research attention in recent years. The MD used a hydrophobic membrane as the separation medium, and the thermal gradient was established to dry the water molecules go through the membrane. In this way, the non-volatile pollutants can be totally rejected by the MD. So MD has the advantage like the high effluent quantities and the high tolerance to salinity and the low fouling tendencies. But if we use the MD in the landfill leachate treatment, we still meet some problems. The first is the penetration of the ammonia, and the second is the fouling. Because there's a lot of foulings like organic, inorganic, and microbial foulings in the landfill leachate. So the fouling issues should be considered. The final one, finally, is the pore wetting. We discussed a lot today. The pore wetting can completely destroy the separation performance of the MD. So it's a very fatal problem. But the application of the MD in landfill leachate treatment is not extensively investigated. So that's still something unknown. For example, the key foulings and the fouling mechanisms. So we need to do more investigations about this topic. The second part is the materials and methods. We build cell-made DCM systems in our lab, and the system contains 3 parts. There's a MD cell, and there is a feedwater circulation system and a distillate circulation system. We gather the distillate weight and conductivity monitored so that we can assess the membrane fouling and the wetting. This is the experiment protocol. The experiment consists of 2 parts. a short-term test and an extended test. In the short-term test, the PVDF membrane was used to treat the mature landfill leachate, and the pH was changed to assess the membrane fouling, to assess the ammonia removal. In the extended test, the PVDF and the PTFE membrane was used to treat the young and mature landfill leachate, and the experiment was extended to 15 days so that we can assess the impacts of membrane characteristics. Okay, the third part is the experimental results. First of all, we investigated the performance of this MD in landfill leachate treatment. From this figure, we can find that the organic rejection rate was generally higher than 98%. The change of the pH did not affect the organic rejection. We also used the fluorescence spectrometer to evaluate the organic removal. The fluorescence intensity of the distillate is less than 0.3% of that in feed water. Hence, we can find that MD is very efficient in removing the organics in the landfill leachate. We also assess the rejection of the metal ions. As we can see in this table, all the five metal ions, including sodium, potassium, magnesium, calcium, and ferric ions, the rejection rate is nearly 100%. Moreover, we can find that the rejection rate was not affected by the feed pH. Because the ammonia is a volatile pollutant, it can penetrate through the membrane, especially in alkaline conditions. So the rejections among ammonia is around 15% at a pH of the 9. When the pH was adjusted to the 5, the rejection rate would increase to 96%. From this figure, we can find that because of the penetration of ammonia, the distillate conductivity increased with the running of the system. So we cannot use the distillate conductivity to assess the membrane wetting. To address this problem, we use the fluorescence intensity to check whether the wetting occurred. Okay, the first and the last 100 milliliter distillate was sampled and detected. The fluorescent intensity was compared. It was found that the fluorescent intensity did not significantly change. This indicated that the membrane wetting did not occurred when the landfill leachate was concentrated by 5 times. The following is the most significant problem investigated. The membrane fouling was from these figures, we can find that the fouling is strongly affected by the feed pH. The specific flux decreased to 0.3 when the pH was feed pH was 9. When the pH was adjusted to 5, the flux reduction was only 13%. Only 13%. The results indicated that the feed acidification can help to reduce the MD fouling. Moreover, the contact angle and the LEP was also measured. From these figures, we can find that the contact angle and LEP, both of them decrease with the increasing pH. We can infer from this result that the membrane fouling is going to compromise the hydrophobicity of the membrane and increase the risk of wetting. To get inside into the fouling, the fouled membrane was characterized by the SEM and the FTIR. we can find that the coverage of the membrane by the foreign layer increased with increasing pH, and we can find from the cross section view that the thickness of the foreign layer also increased with increasing greater pH. In this page, we show the EDS results and FTIR results. From the EDS results, we can find the signals of the inorganic elements increase with increasing pH. From the FTIR results, we find that the typical peaks of the membrane was weakened, but the peaks of organic was increased. From this result, we can conclude that both organic and inorganic components have already deposited on the membrane. To further understanding the foreign, the chemical cleaning was performed and the cleaning waste was analyzed. There are two interesting points in this result. First, we find that there are a lot of organics in the acid cleaning waste. Usually, we use the alkaline cleaning to remove the organic foreigns. It's generally considered that the acid cleaning is less effective in removing the organic foreigns, but we find that there are a lot of organics in the acid soaking solution. The second point is that when the pH increased from 7 to 9, the organics in the cleaning waste increased rather than decreased. From this result, it can be found that organic deposition was enhanced at a low pH condition due to the reduced electronic repulsion. However, the organic deposition was also enhanced at the alkaline condition due to the cohesion of the organics and the inorganic foreigns. This is something we find is new. Okay, after that, we conduct an extended test of the landfill leachate treatment with DCMD for 50 days. We also assess the performance and the foreign. From these figures, we can find that the organic removal performance is very good over the whole duration. The PTFE outperformed the PVDF, and is the distillated COD is generally less than 10 microgram per liter. We also investigated the removal of the ammonia. The penetration of ammonia also exists and result in increased distillate conductivity. The penetration of the ammonia was not affected by the membrane types. The young landfill leachate caused more ammonia penetration due to the higher ammonia concentrations in the filtered water. The membrane fouling was investigated in terms of the flux reduction. For PVDF, the young landfill leachate, which contains more biopolymers, caused more flux reduction during MD. For the PVDF, the mature landfill leachate caused more severe fouling because it contains more humic acid and inorganic ions. To better understand the fouling, the SEM images of the fouling membranes was taken. There are a lot of crystals on the membrane followed by the mature landfill leachate. For the PVDF membrane, the young landfill leachate caused much more organic deposition, resulting in a very thick fouling layer. This is consistent with the most severe fouling in landfill leachate treatment with the PVDF membrane. Based on this result, we can draw some simple conclusions. MD is able to effectively reject organics and metal ions in the landfill leachate. And the following is the dominant. The membrane MD following is a membrane dependent and pH dependent. The following is dominated by the co-deposition of the organic and inorganic followings at the neutral and alkaline conditions. Feed acidification is able to improve the rejection of ammonia and reduce MD following. Okay. Thanks a lot for your attention. Special thanks to gives to Dr. Yang and my student Ling Xiong. And thanks to the NCFC for the financial support. Thank you very much.
Oh, sorry, I forgot to unmute myself. Thank you so much for that great talk, Feng Shu. So if anyone has questions, feel free to write them in the chat. I see we have one here. So Fei Gua is asking, thank you for the interesting talk. What is the maximum concentration of landfill leachate by MD in your experiments? Is this a ZLD process?
Okay, can you repeat the question again?
Yeah, sorry. What is the maximum concentration of landfill leachate by MD in your experiments? So how high of a concentration did you get to? And also, is this a zero liquid discharge process?
Okay, I think he means some characteristic of the landfill leachate. Okay, the COD concentration is about 2,000 milligram per liter, and ammonia concentration is about 200 to 300 milligram per liter, and with the temperature of the MD we use is 60 C centigrade. Okay, is that okay?
Yeah, and then I think that he was also asking how much did you concentrate that solution? So do you know the final concentration of your feed after MD treatment?
The landfill leachate was concentrated for 5 times. Yeah, in the short-term test. In the extended test, the concentration factor is about 5 to 10. Okay, we performed the experiment for 50 days.
Great. And do you think that it could be used for actually zero liquid discharge all the way to a solid feed concentrate?
I think it's not now because it's quite expensive and it's energy demand is very high. So in our country, we now use the burning to deal with the municipal solid waste. So some waste energy can get from this for example, rubbish burning. So if we can use this solid waste, waste heat, maybe we can use the MD to treat the landfill leachate.
Great, thank you. Let's see. I was going to ask one quick question. So you looked at the effect of pH to improve ammonia rejection and improve fouling. Do you think there are any other operating conditions you could change to improve ammonia rejection or fouling, or both?
Okay, I think there's 2 aspects we can do to reduce the fouling. For example, we can do some pre-treatment. We can use the oxidation and coagulation to reduce the fouling. The second way is do some optimization of the parameter factors. For example, the flux and the temperatures and circulator velocities. We can get them optimized. This is something we can find out here.
Great, thank you so much. Okay, so we're still waiting to see if we can get our last speaker in. We don't have them here now. So if anyone has any questions for any of the speakers, feel free to enter those into the chat or the Q&A. and we can do a panel here. I'll ask one more question for you, Fengshu. Do you think anti-fouling membranes could really improve the process a lot in MD? Do you see a place for those in applications like this? Or are operating conditions better?
Okay, I just think that DCMD is the most simple configuration. We can easily establish such a system in our lab. But personally, I like the vacuum MD better. Yeah, I also did VMD system in my lab. I used it to do ANMDBR. It's an aerobic membrane distillation bio MBR. You know, we use the MD membrane to replace the ultra or to replace ultrafiltration or microfiltration. So we can build a new system to treat some organic high concentration organic with the water, so that we can generate some CH4, the methane, so that we can use the recover the energy from the wastewater, so that the energy problems of the MD maybe can be solved to some extent. So now I was trying to do more research on the VMD. Okay.
Interesting. Yeah, I think that might be promising too. Okay, so we have a couple more questions in the chat for you. So Alicia is asking, do you plan to scale up MD for landfill leachate treatment?
Yes, yes, but the scaling up is not just a simple problem. It needs a lot of investment. Yeah. Now we cooperated with landfill leachate. They are we now just do some experiment in the lab, and for the next steps, we will do a bigger, maybe pilot investigation in their landfill leachate. Okay.
Nice. Yeah. And so then as a follow-up to that, she asked if MD can be a competitive option compared to existing processes.
I read some. I read a lot of articles. I think it's saying that when there is waste energy, waste heat, the MD is comparable to reverse osmosis. In China, we use the DCM. We use the MD to use the reverse osmosis to treat the landfill leachate a lot. But there's still lots of problems. For example, the system is very complicated. It requires a lot of maintenance. This will stop the application of the membrane technologies. So I think if we can use the, I think the MD is a much simpler system. I think it's a one-step process because the MD can remove the organic ions, just lots of pollutants, just except ammonia. So I think MD is much better than our reverse osmosis. But the only problem is the heat. the energy. Okay.
Yeah, great. And then maybe we'll just do one last question and then we'll close the session here if we don't get our final speaker in. So Fei Gua is asking, as ammonia is very smelly, do you think the MD system should be sealed in a closed system?
Of course. And if it can be sealed in a closed system, it will be good. You know, in my cities, all the wastewater treatment plant was partially sealed. You know, the gas is smelly, so we do a lot of work to treat the smell gas. But I think I have another work about MD is to recover the ammonia from the landfill leachate with the two stage of MD. The first stage, the pH was increased so that the ammonia can go through the MD membrane. In the second stage, the pH was decreased. Then the ammonia was absorbed. Then in the second stage of MD, then the pure water goes through the membrane and the ammonia concentrated in the middle, so that we can recover the ammonia. I'm doing that work in my lab, but the progress is not very good.
Yeah, interesting stuff. Okay, great. So thank you so much to all our speakers. Yeah, thank you for the extended Q&A session there. That was great. I think with that, we'll end the session just a little bit early here. And yeah, thank you all. So.
Alison, Aaron here. That it all went well, so you may stop the recording now. I think where you have the host access, you can stop the recording.
Okay, I think maybe Wenwei